Hello and welcome to this chemistry short, where we're going to be looking at a question from the American Chemistry Olympiad. So this question is talking about a weak base, which is pyridine, which is C5H5N. It's a weak base, and it's given the Kb value is 1.78 times 10 to the power negative 9. Question A is calculate the OH minus and the pH of a 0.240 mole per liter solution of pyridine. So in this case, we're going to write down the dissociation for pyridine. So it's C5H5N. And we're going to add water, and then it's going to give us C5H5NH plus of OH minus. So therefore, our Kb expression for this reaction would be the concentration of C5H5NH plus multiplied by the concentration of OH minus divided by the concentration of C5H5N. Alright, so for this, we're going to assume that since the Kb value is very low, that there is virtually no change to the concentration of C5H5N in the solution. Therefore, at the end, the concentration of C5H5N will still be approximately 0.240 mole per liter. So, and we also know that the OH minus concentration is equal to the C5H5NH plus concentration, assuming that the water dissociation is not significant. Okay, so therefore we can say that Kb multiplied by the concentration of C5H5N square root is equal to the concentration of OH minus. And therefore, if we plug some numbers into the calculator, so we have Kb equals to 1.78 times 10 to the power negative 9 multiplied by 0.7 square root. So therefore, we can see that the OH minus concentration is equal to 2.067 times 10 to the power negative 5 mole per liter. And that will give us a pH of 9.32, is our pH for this solution. Alright, looking at part 2 for this question. Part number 2 is calculate the pH after 20 milliliters of HCl solution has been added. So this titration is a weak base strong acid titration. So if we look at the graph for the weak base strong acid titration, it is going to look something like it's not a good drawing. Yeah, it's not a very good drawing, but it'll look something like that. Okay, so it's going to have a weak base, and then as it reaches the equivalence point, it's going to be a sharp drop in the pH, and then it's going to flatten out. Okay. So in this case, we're going to find out the amount of HCl that's been added. So we just write part A, part B. So the amount of HCl that's been added is equal to 0.02 times 0.102. And that is equal to 2.4 times 10 to the power negative 3 moles. Alright, so we can also calculate the amount of we calculate the amount of pyridine that was in the solution by using N equals Cv. So that's N of pyridine, so it's C5H5N. That is equal to 0.02 times 0.240. That is equal to 4.8 times 10 to the power negative 3 mole. And we know that when C5H5N, so we just write the equation for the neutralization. So we're just going to say this is going to react with hydronium ions, and it's going to give us the conjugate acid as well as water. So therefore, since there's 2.4 times 10 to the power negative 3 moles of HCl, 2.4 times 10 to the power negative 3 moles of C5H5N is going to react to get to our conjugate acid. Therefore, we're going to have the amount of C5H5 and NH plus is equal to 2.4 times 10 to the power negative 3 mole. And the amount of C5H5N is equal to 4.8 times 10 to the power negative 3 minus 2.4 times 10 to the power negative 3, which is also 2.4 times 10 to the power of negative 3 mole. To find the pH, we know that since we have both the acid and the conjugate base, this is going to be forming a buffer solution. So that's when both the conjugate base and the acid is present in the solution. So therefore, small additions of acid or base is not going to cause a huge change in the pH. So therefore, we can use the Henderson-Hasselbalch equation to find the pH. So that's pKa equals to pH plus log of the concentration of HA, which is the acid over that of the base. So in this case, we can find out the total volume. The total volume is 20 milliliters plus 20 milliliters. So that's a 40 milliliters. So therefore, the pKa, which we can find by, the pKa we can find, so we can say that pKb is equal to negative log of Kb, which is equal to negative log of what we have up there, which is 1.78 times 10 to the power negative 9. Which is equal to 8.75. So therefore, pKa is equal to 14 minus that, since pKb plus pKa is equal to 14. So pKa is equal to 14 minus answer, which is 5.25. So therefore, the pKa is 5.25. So we're going to plug that into our Henderson-Hasselbalch equation. So 5.25 is equal to the pH, which we don't know, plus log of the acid, which is 2.4 times 10 to the power negative 3, divided by the volume, which was 0.04, divided by 2.4 times 10 to the power negative 3, divided by 0.04. They will cancel each other out, so therefore we see that pH equals to pKa, so therefore pH is equal to 5.25 for question number 2. Alright, so now we look at question C. Question C is talking about, question BI, sorry. BI first, So BII. Calculate the pH at equivalence point. Okay, so at equivalence point, there's only going to be the conjugate acid present, since all of the conjugate bases already reacted with the excess acid. So therefore, we're going to have C5H5NH+. That is going to react with some water to give us C5H5N as well as some hydronium ions. Therefore, the solution will be acidic at the equivalence point. In this case, we need to find the Ka, since we're talking about the conjugate acid, C5H5NH+, which we already have the pKa, so we can say that Ka equals to 10 to the power of negative 5.25, and that is equal to 5.623 times 10 to the power of negative 6, sorry, no unit. Right, so now we can write. So we know we can write the equilibrium expression for the dissociation of the acid. So that's C5H5N multiplied by hydronium divided by C5H5NH+. However, we know that there's only going to be C5H5N at equilibrium, not equilibrium, at the equivalence point, because all of the not C5H5. There's only going to be the only C5H5N is going to be from the dissociation of the conjugate acid, because all of the original C5H5N has been reacted with the hydronium to form the C5H5NH+, and therefore the only C5H5N that is in the solution is that from the dissociation of that conjugate acid. So therefore we can say that 5.623 times 10 to the power negative 6 multiplied by the concentration C5H5NH+. We do need to find that. Okay, so at the equivalence point we need to add at the equivalence point. Okay, equivalence point. If equivalence point, we have in total we have 4.8 times 10 to the power negative 3 moles of C5H5N. So therefore we need to add 40 milliliters of HCl. 40 milliliters of HCl. Therefore the total volume is 60 milliliters. Since the total volume is 60 milliliters, we can find the C5H5NH+ concentration, since we know the amount is 4 times 10 to the power negative 3, and that is divided by 0.06. And that is going to be equal to hydronium. So hydronium comes out to be 6.707 times 10 to the power of -4 mole per liter. Sorry, I can't fit it. We have 6.71. And that's our answer. And if you want to find the pH at the equivalent, just take the negative log of that. Negative log of that will give us pH equals to 3.17. Alright, so that is question BRI done. So let me just rub out what we did here for part A. So we're going to continue with part C. Looks like we're talking about solubility here. So if MgCl2 is added to the 0.240 molar solution of pyridine, what's the minimum Mg2 plus at which MgOH2 will precipitate? So in this case, we're going to write this. We're going to write the equation for the dissolution of MgOH2. So MgOH2 is a solid that's going to be in equilibrium with its ions, which is Mg2 plus and OH minus. So if we write the Ks expression, we're going to get Mg2 plus times OH minus squared. Alright, so we know, we know that is the same solution of pyridine, which was in part A, and we found that the the OH minus concentration in the solution of pyridine was OH minus equals to 2.07 times 10 to the power -5 mole per liter. So it's very simple here, so we can find the Mg2 plus required just by rearranging the Ks expression. So 5.6 times 10 to the power -12 equals to Mg2 plus times 2.07 times 10 to the power -5 squared. So that gives us an Mg2 plus concentration of 0.0131 mole per liter. That is required for the precipitation to occur. Looking at question D, if we just here. Question number D. So for a solution with Mg2 plus concentration is 0.1 mole per liter and C5H5N equals to 0.240 mole per liter. 0.240 mole per liter. What must the C5H5NH plus concentration be to just prevent the precipitation of MgOH2? So once again, just to prevent the precipitation of MgOH2, which means that it's just the solution is just saturated, which means any more addition of the ions will cause the precipitate to form. So therefore, at this point, the solution is saturated, so the product of the ions will be equal to Ks. All right, so for solution with so we have. So in this case, since we have both of the ions will be so both of the ions, so in this case we have the base and the conjugate acid. So since both of them will exist in the same solution, this will form the buffer solution, and the pH of the buffer solution and hence the concentration of OH minus ions will be depending on the relative ratio of the conjugate acid to the conjugate base, which is by the Henderson-Hasselbalch equation. So immediately we can use our Ks expression to find the minimum amount of OH minus. Not minimum in this case. In this case, would be the maximum OH minus that can exist in order to just prevent the precipitate of the MgOH2. So in this case, we say that 5.6 times 10 to the power -12 equals to 0.1 times of OH minus squared. So we should find that our OH minus concentration comes out to be 7.483 times 10 to the power -6 mole per liter. And therefore this is going to give us a pH of, so negative log of, so pH here is 8.874. So in this case, we're going to find what is the concentration of the conjugate acid and the conjugate base in order to give a pH of 8.874, and we're going to be using the Henderson-Hasselbalch equation to do so. So therefore, we know the Ka value of pKa is So we know the pKa value is we know the Ka value, so therefore we know the pKa value, which was 5.25. That is equal to the pH, which is 8.874, plus log of the conjugate acid, concentration of conjugate acid, which we don't know. So that's C5H5N divided by 0.240. Alright, so now we can solve to find the concentration of C5H5N. And so therefore 10 to the power of negative 3.4, 10 to the power of negative 3.624 equals to concentration of C5H5N divided by 0.240. So therefore the concentration of C5H5N is equal to equal to 5.70 times 10 to the power of negative 5 per liter. Alright, and that's our final answer for this question, okay? And that's it for the short, a little bit of a short on equilibrium. So this really covers the buffers. It really covers all of the topics for equilibrium. It covers solubility. It covers titrations, and it also covers the acid-base principles. So I hope you enjoyed this little short, and I hope it was helpful for you to watch this video. And I hope to see you all in the next one. Thank you. Bye.